Nitte Meenakshi Institute of Technology, popularly known as NMIT.
Hi everyone, my name is SIDDALINGAPPA P KODIGADDI. I am working as an assistant professor in the Department of Aeronautical Engineering, Nitte Meenakshi Institute of Technology, Bangalore. So here we are in the Aerodynamics laboratory of Department of Aeronautical Engineering. So we have the test facility which is called low speed subsonic wind tunnel. So here today we will be demonstrating the few experiments that can be conducted using this particular facility. There are basic types of many wind tunnels which are available. One is the subsonic wind tunnel, the transonic wind tunnel, the supersonic and the hypersonic wind tunnel configuration. So these are basically depending on the test section Mach number, the velocity of the air in the test section of the particular wind tunnel. So basically the wind tunnel uses the convergent, the constant area duct and the divergent duct to make the flow inside the tunnel. So when it comes to the classification of wind tunnel based on the flow of air into the tunnel and out of the tunnel. So we have the open circuit and the closed circuit wind tunnel. In the open circuit wind tunnel, the fresh air will come from the atmosphere and used air can be leading to the atmosphere. But in the closed circuit wind tunnel, there will be a usage of like the recirculation of air inside the tunnel will be happening. And when it comes to the relationship between the test section and the atmosphere, if it is closed, it can be closed type wind tunnel, and if it is open to the atmosphere, and it is called as the open type of atmosphere. And as per the applications, we have industrial type and the academic type of wind tunnel. So based on the classification and the things what we have discussed earlier, so the wind tunnel facility which we have in our laboratory is the low speed subsonic open circuit closed type wind tunnel, which is for the academic purpose and also the research and development purpose. So now the thing is, like, we'll discuss the basic parts of this low speed subsonic wind tunnel facility available in our department. So as soon the air enters into the wind tunnel, the low speed wind tunnel, so first we'll have a settling chamber, and that will be comprising of the honeycomb structure and the meshes. So honeycomb structure basically it can be of a square, the circular or the hexagonal section with that. So basically to decrease the turbulence in the air which is entering into the wind tunnel layout. So one thing is the air which is entering the test section or the convergence section should have the very less turbulence, we can say that zero turbulence. So to achieve that, we will be using the honeycomb structure here. So in this tunnel we are using the square type of honeycomb structure and also the meshes. Basically it will be able to avoid the foreign particles to enter into the wind tunnel layout. The basic principle behind the working of wind tunnel, low speed wind tunnel, is the Bernoulli's principle and the conservation of mass. So here, according to that, when the flow goes through the convergent ducts, the properties like the pressure decreases and the velocity increases. So based on the velocity that should be available at the test section, so we will be designing the convergent duct or the effuser. So here in the facility which we have in our lab has the compression ratio of 9:1. So where the area of the convergent duct, the reduction in the area of the convergent duct from the entry to the exit will be 9:1. That means the 9 times the air will be compressed to achieve the required velocity at the test section. So the effuser will have the bell mouth structure. So it will be able to compress the flow smoothly at the corners so that the smooth deviation of the flow will be happening here, so that the turbulence, what all the turbulence which can be caused during this compression can be avoided. So after the effuser, the air will be entering into the test section. Now it will have a required pressure, the velocity. So now the test section is basically the constant area duct. The facility which we have has the test section dimensions of 600 mm by 600 mm square and the length of 2000 mm. And the test section is the place where we place the object of interest for getting the experimental data. So here it is quite transparent so that you can visualize the flow inside the tunnel. So once the test is done, the air will be entering into the diffuser. Basically the diffuser will have a increased cross-sectional area. So as we come from the inlet to the exit of it. So now the thing is, the used air, it has to leave to the atmosphere, so that the diffuser plays a very important role in this by increasing its pressure and decreasing the velocity. So basically we have the square cross section at the entry of the diffuser, and here it's been converted into the circular cross section. Because we have the single axial fan to make the flow inside the tunnel. So this axial fan will be rotating at a certain RPM, and it is directly proportional to the velocity of the air inside the tunnel, because the mass flow rate inside the tunnel will be depending on the speed of this particular axial fan. So in our wind tunnel facility, so we can conduct the experiments that can get the pressure distribution around any object of interest, and the loads which are acting on that, and the movements which are acting on that, and the flow visualization around the object of interest, as well as the surface flow visualization. So these experiments can be done with the data acquisition system available. So to get the velocity data inside the tunnel, so we have the pitot static probe, so which is placed near to the entry of the test section. So where the pitot static probe will be working based on the principle of Bernoulli. So basically the pitot static probe will give the data like the total pressure and the static pressure of the flow, and in turn it is connected to the U2 manometer, so that the manometer head can be calculated, and we have the relation between the pressure and velocity from the Bernoulli's equation, which is P plus half rho V square is equal to constant. It is nothing but the static pressure plus dynamic pressure is equal to the total pressure. So with that relation, we will be able to find out the velocity of the flow inside the tunnel. The pressure distribution around the object of interest can be calculated by using the experimental setup here. One is the conventional multi-tube manometer technique to get the local static pressure on the around the object of interest, and we have the 32 channel pressure scanner also, where the exact pressure value can be calculated over a different angles of attack, or for the different speeds, or at the different time. So here conventionally we have the manometer, multi-tube manometer channel. So it can calculate the pressure at 15 different locations around the object of interest. So one manometer tube is connected to the test section wall to get the free stream static pressure. So there with the pressure difference like the local and the static. So one tube is connected to the test section wall, there we get the free stream static pressure, and the local static pressure we can find out using 15 different manometer tubes around the object of interest. So with this pressure difference, we will be calculating the pressure coefficient at different locations on the object of interest. So to get the pressure coefficient data, so here in this tunnel we can calculate the pressure distribution around the three different models. One model is the circular cylinder, and the second model is NACA 0012 airfoil configuration, which is a symmetrical airfoil, and and the NACA 2412 airfoil configuration, which is the cambered airfoil. So to get the local static pressure around the object of interest, here you can see that we have a 15 pressure ports which are the drilled holes perpendicular to the local area at 15 different locations, and internally they are connected to these metal tubes, and we have a number on it. And now these metal tubes will be connected to the flexible manometer tubes that are here. So with this we can have the manometer head from the multi-tube multi-channel manometer here. To enhance the accuracy and to reduce the human errors, we have the digital 32 channel pressure scanner. So basically we can have the accurate pressure values at different locations around the object of interest with this particular data acquisition system, and it is connected to the computer so that at any time or over the different time or different time intervals we can have the pressure data around the object of interest, and simultaneously we can change the velocity inside the test section, and the continuous data acquisitions can be done. And also we have the 6 component balance to get the 3 forces and the 3 moments around the airplane. So here this can be done by using the digital 6 component balance, where we can get the data like the 3 forces, lift, drag and the side force, and the 3 moments, pitching moment, yawing moment and the rolling moment. To conduct different flow visualization experiments, so we have the 2 setup. One is for the fluid flow visualization, where we can see how the flow is disturbed when we place the object of interest into the flow, and we have the other setup which is the tuft flow visualization. It is basically for the surface flow visualization, where we can see that exactly what is happening on the surface of the object of interest. So here to conduct the smoke flow visualization test, we have the smoke flow generator. Basically it produces the highly dense white smoke, and here we are using the paraffin liquid. So we are going to heat it up to a certain temperature. Now the liquid will be converted into a highly dense white smoke, and we have the facility to take that particular smoke onto the object of interest inside the tunnel, and we can have the flow visualization around the cylinder bodies, the different airfoil configurations like symmetrical cambered airfoil configuration at different speeds, different angles of attack, and exactly we can capture the location where the flow separation is happening and the formation of vortices. To conduct the experiment of tuft flow visualization, so we have the blended wheel body here, where the tufts are the small strings which are attached to the surface of the blended wheel. So here the basic principle is the tuft changes its orientation based on the direction of the flow which is going around that. So with that, the basic principle, so we can actually visualize how the flow is going to deviate on the surface of this particular blended body at different speeds, and also the angle of attack can also be changed. So here when it is at a higher angle of attack, we can see that the flow separation will be happening near to the leading edge and the top surface of the airfoil, and the tufts will be coming away from the surface. That means the flow separation is happening, and also based on the vortex formation, these tufts will be changing its orientation. Okay, so with that we can actually see that how the flow is changing its direction on the surface of this particular object of interest.